All right, welcome back, everybody. Today we're going to do section 5.5, and in this section we're going to get the graphs of all the rest of the trigonometric functions. So the last section we did the graphs of sine and cosine. Now we're going to do the graphs of the rest: tangent, cosecant, secant, and cotangent. So yeah, I'll pull up the slides and let's get started. So here's the overview. We're going to review some properties of tangent, and then we're going to look at the graph of tangent. Then we're going to talk about an important limit property. And this property of limits is what's going to make graphing the other trigonometric functions much more straightforward and easy. Then we'll review properties of cotangent. We'll look at the graph of cotangent. Then we'll do properties of cosecant and secant, the graphs of those things, and then transformations of those graphs. So it sounds like a lot, but if you are comfortable with sine and cosine and the unit circle in general, then these ones actually come out pretty quickly. So let's get started. Reminders here. So remember that tangent is sine over cosine. And because we're going to be graphing in the xy plane, our input variable is x and our output variable is y. So just a reminder, that's what tangent is. Now, the domain of the tangent function is not all real numbers, because remember, tangent is basically the slope of that ray that passes through the origin and the point P. So the slope is undefined if you have a vertical line. So the domain is not all real numbers. In particular, the domain is everything except for odd multiples of pi over 2. So tangent is defined except for pi over 2, 3 pi over 2, 5 pi over 2, 7 pi over 2, and then also the negatives and so on. Now, because tangent is a ratio, what that means is that as you approach those points that are not in the domain, what you're going to get is you're going to get a vertical asymptote there. So you'll have a vertical asymptote for each one of these values of x, for each one of these odd multiples of pi over 2. And then the other thing I want to remind you of is that the period of tangent is pi. So it's a little different than sine and cosine. The period for tangent is just pi itself, not 2 pi. All right. So this is just a definition. Some of you may have seen this definition before. If you haven't, you certainly will later. So I'll talk a little bit about this notation, a little bit about limits. But we say that the vertical line x equals a is called a vertical asymptote of the curve if f has an infinite limit from the left or the right, or both, as x approaches a. So this here is actually using limit notation. This thing right here, this symbol, that's actually what we call the limit operator, this one over here as well. And the limit operator essentially tells you to take points that are closer and closer to a point. That's what it means. So here in this case, let me zoom in a little bit. See how it says, oops, uh, as x goes to a, and then it's like a superscript minus sign. What that means is you're going to take values of x that get closer and closer to the number a, but you're going to come from the left side, from the left, the negative side, if you will. That's what that means. So if you keep picking values of x and plugging them into f of x, does that function value, f of x, approach negative infinity or positive infinity? That's what we're asking. So if as you get closer to that point A from the left, the function shoots up to positive infinity or it shoots down to negative infinity, then you're going to have a vertical asymptote there. That's what it means. And then also you could have that behavior from the right. So you can also talk about coming toward a point from the right. And if your function blows up to infinity or blows up to negative infinity, that's going to be a vertical asymptote. So all together, that's what it is. That's what it is. If this notation is a little too cumbersome or it doesn't make sense yet, that's okay. You'll see it in Math 4. You'll also see it in Calc 1. But for now, it basically just means, hey, if your function is going to blow up and go to positive infinity or negative infinity, it could go like this, it could go like this, it could switch and go both ways like that, right? If any of those things are happening, you've got a vertical asymptote. Okay. Now, what I've got here is basically a table of values for sine, cosine, and then tangent, correspondingly tangent, right? And we're just going to look at how these numbers change as we get closer to these asymptotes, right? So let's start here. If you start at pi over 3, which is about 1.05, we know that the value of sine is root 3 over 2. It's a standard angle. And the value of cosine is 1/2. And then if you do the tangent of that angle, remember tangent is just sine divided by cosine. So when you do sine divided by cosine, you're going to get square root of 3, which is about 1.73. Okay, now what we're going to do is we're going to take points that get closer and closer to pi over 2. So going from pi over 3, getting closer and closer to pi over 2, and we'll see what happens. So when x is 1.5, oops, when x is 1.5, sine is about 0.9975, cosine is about 0.0707. So when you take the ratio of those two numbers, you get 14.1. Now, at 1.57, tangent becomes 1,255.8. At 15707, tangent becomes 10,381. And then at pi over 2, it's undefined because that's when you have the vertical line. So what this is telling us is that if you look at these numbers over here, as x approaches pi over 2, from which side did we do? From the right? From the left, I apologize. As x approaches pi over 2 this way, from the left, then what happens is tangent blows up to infinity, blows up to positive infinity. It keeps getting larger and larger and larger. And again, you should always be asking for some kind of intuition with these types of things, right? This makes sense because if you think about the slope of this line, right? The slope of the line that is my Apple Pencil. Here, maybe I'll do this actually. Think about the slope of this line. As the line tips upward, the slope gets larger and larger and larger and larger and larger until it's gigantic. Now the slope is like 20 million, now it's 20 billion, and now it's like 20 quadrillion, right? And so what happens is as the line tips upward, as the angle approaches pi over 2, the value of the tangent function, the value of this slope, blows up to positive infinity. That's the idea. Okay, so how does that affect the graph? Well, basically as you get close to pi over 2, tangent's going to shoot up to positive infinity. So here's what it looks like for one period of the tangent graph. So this is the graph of tangent on, I'm sorry, not one period. This is just the graph from negative pi over 3 to pi over 3. So here you go. Here's pi over 3. Let me get a different color. Come here. Let's do this pink. Okay, so like from pi over 3 to pi over 3, you can plug in some values for x, plug them into sine and cosine, and then that'll let you compute tangent, just like we did a moment ago. And so start at 0, and then your tangent curve starts to do this. And if you go this way, it'll start to do this. And then what happens is it keeps growing and growing and growing as x approaches pi over 2. And as x approaches negative pi over 2. So what you end up getting is you end up getting asymptotes at negative pi over 2 and pi over 2. Asymptotes just like this. And so the graph keeps approaching, oh, there you go, approaching infinity as you get close to those numbers. But that's pretty much the idea. Evaluate sine, evaluate cosine, compute that ratio, and that'll tell you what tangent is. So what does it look like on the whole real line? Well, remember the period for tangent is length pi. So one period is basically going to be graphed on the interval negative pi over 2 to pi over 2, and then it's just going to repeat, and then it's going to repeat, and keep going. So all together we have this. And this is what the graph of the tangent function looks like. This is what it looks like. So in the middle here, this is what we were just observing in the previous slide. And then it's just a repetition of that graph every pi radians. It just repeats. There we go. So that's what it looks like. And again, notice you've got an asymptote at all the odd multiples of pi over 2, like I was saying before. 1 pi over 2, 3 pi over 2s, 5 pi over 2s. and then also the negatives, right? So negative pi over 2, negative 3 pi over 2's, negative 5 pi over 2's, and that's what it looks like. So that's about it. That's about it for tangent. How do you graph it? You can just test a couple of points. There's not as much like wobbling as you can see with tangent, so it really just kind of looks roughly like what you see here on the screen. Yes, and then there's this note at the bottom, and that's going to lead me into the next slide. So tangent has asymptotes at odd multiples of pi over 2, and it has zeros at integer multiples of pi. So let me point those out right here. Notice here that, let me go with pink. At 0 pi, the value of tangent is 0. At 1 pi, the value of tangent is 0. At 2 pi, the value of tangent is 0, and so on and so on. Negative pi at 0, negative 2 pi at 0. So at all of the integer multiples of pi, 1, 2, 3, 4, 5, 6, negative 1, 2, 3, 4, 5, 6, 0, and so on, you're going to have a 0 there. So tangent is 0 at integer multiples of pi. Right. Why is that important? Because we're going to need that to help us graph cotangent. And this property, looking at the asymptotes and the zeros, we're going to need that as well to graph cosecant and secant. All right, so this is the important limit property. This is the one that you need to be able to make sense of. We'll talk about the intuition here in just a second, but if your function has an infinite limit as you approach a point A, then the limit of the reciprocal function is going to be 0. So in other words, if x approaches a of f of x and you get an infinite limit of some sort, then what that means is if you were to instead look at the reciprocal function and take the limit of the reciprocal function, you're going to have 0 at that point. That's the idea. So let me try to make intuitive sense of this before we go to the next slide. Think about it like this. What if my function values, how do I want to write this? Okay, let me write it like this. So if f of x ends up equaling something like, we'll start with like 10. So let's say I'm approaching some number like pi over 2 for tangent, right? X is going to pi over 2. Well, if I got the number 10, I got the number 10. Now if I get closer to pi over 2, I might get 100. And then I would get 1,000. And then I would get 10,000. And then I would get 100,000, ... right? So basically, as I keep approaching this number, my function values blow up to infinity, really, really large numbers. So what this limit property is saying is, hey, if you look at the reciprocal function, then 1 over f of x is going to be equal to 1 over those really big numbers. So now you're going to have like 1 over 100, which is pretty small. And then you'll have 1 over 1,000, which is even smaller. And then 1 over 10,000, which is even smaller. And 1 over 100,000, which is even smaller. And so what happens is that 1 over f of x starts going to 0. So in other words, if your regular function has an infinite limit, then the reciprocal function is going to have a 0 limit. That's the idea. And the intuition is basically take the reciprocal of really big numbers and you get really tiny numbers. That's the intuition for it. How is that going to help us? Because that allows us to use, come back. It allows us to use the graph of tangent here to graph cotangent, because cotangent is just the reciprocal of tangent. So what this important limit property tells us is, hey, when tangent has an infinite limit, cotangent is going to have a 0. And when tangent has a 0, cotangent is going to have an infinite limit. So all of these points of interest that we've marked here, all of these asymptotes and all of these zeros, the behavior of cotangent is going to be switched at those points. So let's take a look. Let's go straight here. Or sorry, let's do this first. Okay. So what's cotangent? It's the reciprocal of tangent, which will give you cosine over sine. The domain is everything except for integer multiples of pi, and we're going to use that property of limits. The period of cotangent is pi. So let's go back here. This is what tangent looks like, and this is what cotangent looks like. Boom. Oh, give it a chance to load there. All right, so that's cotangent, that's tangent. Cotangent, tangent. Sorry about the little blurriness. My iPad has to like think every time I go to the next slide. Um, but that's what it looks like. So let's investigate, right? Let's investigate what this graph is doing. We have all of these asymptotes. We have asymptotes at all of the integer values of pi. Now think about that for a minute. So at the integer values of pi, cotangent has an asymptote. And that makes sense because if you think about the tangent graph, all the integer values of pi are where tangent has zeros. So because tangent is going to 0 at these points, cotangent is going to go to infinity at these points, or negative infinity. And that's exactly what's happening here. Exactly what's happening. Now, also compare this to where all the zeros are occurring. So if I look at the zeros of cotangent here, so like negative, negative 3 pi over 2's, negative pi over 2's, or negative pi over 2, pi over 2, 3 pi over 2's, 5 pi over 2's, cotangent has a 0 there. So that means that tangent must have an infinite limit at those points. Let's check. Oh, it does, right? It does. And it's exactly because of that important property of limits. That's really it. So if my function has a 0 at some point, then if I reciprocate that function, I'm going to have an infinite limit there. If my function has an infinite limit at some point, then if I reciprocate my function, I'm going to get a 0 there. And that's a really, really powerful theorem, a powerful proposition to keep in mind, this one right here, because it totally informs what the graph is going to look like. And you don't really need to graph much more, right? You can basically deduce what the graph of cotangent is going to look like just by looking at the graph of tangent and reciprocating the behavior. And you can do that for all of the other points as well. It's not just infinite values and zeros. You can look at you're basically just reciprocating every number, every output value. And that's how you graph cotangent. And that's the idea. All right, so now let's talk about cosecant and secant, because I feel like these ones are actually the more fun ones. And one of the things I love asking in my calculus classes is how many students can graph cosecant and secant if I were to just say, can you graph it right now? And most students are like, oh man, probably not. But then if I ask, could you graph sine and cosine? Most students are like, oh yeah, I could graph sine and cosine. And I'm like, great, because if you can graph sine and cosine, then you can graph cosecant and secant. You just use that important property of limits we talked about. Graph cosine or graph sine, graph cosine, and then look at the reciprocal behavior. If sine has a 0, then cosecant is going to have an infinite limit. If sine has an infinite limit, which it doesn't, then cosine would have a 0. So cosecant would have a 0. So cosecant isn't going to have any zeros. So we're going to see all of this. We're going to see all of this just pop right out of the graph. Um, so what's the tip? Like, how do you actually graph cosecant and secant? The easiest way is to graph sine or cosine first. So once again, you just have to be comfortable with sine and cosine. If you can graph those, you can graph their reciprocals. I guarantee it. So what do you do after you graph the corresponding non-reciprocal function, like sine or cosine? Use that reciprocal property of limits and the reciprocal properties of numbers to sketch the reciprocal function itself. So here we go. Let's start here. This is the graph of sine of x. And nothing too fancy here, it's just a standard sine graph. Now, this is the graph of sine of x and cosecant of x. Boom. There it is. So I'm going to just pause here for a minute. I want you to look at this graph and just think about it. Think about it on your own for just a minute. All right, now try to say something out loud to yourself that you observe about this graph and how it's related to the graph of sine. Okay, now let's look at it together. One of the things I noticed right away is that there are asymptotes. So there are asymptotes for cosecant, and there weren't any asymptotes for sine. But that makes sense because the domain of the sine function is all real numbers. The sine function can process any real number you give it, and it will give you an output. But here, that's not the same for cosecant because cosecant is the reciprocal of sine. So if sine is ever zero, then we're going to have an asymptote there. There's going to be a problem, right? So look at this. When does sine equal zero? Well, sine is equal to zero at all of the integer multiples of pi. There you go. So sine is zero here, 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 here. So that means that cosecant is going to have asymptotes at all those points. Boom, which it does, right? So here's these points. Sine is zero, sine is zero, sine is zero, sine is zero, sine is zero. So that basically means cosecant is going to be infinite, or it's going to have an infinite limit at that point. Now, for the rest of the cosecant graph, you just take the reciprocal of the sine function. So here, check this out. Let me use this point as an example. Okay. Yeah, I'll go back to this point right here. So notice that here, as I approach this point from the left, I'm getting numbers that are much, much closer to zero. So the outputs are, starting up here and they go down, 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 down to zero. All right. So if my numbers are going down to zero, then the reciprocal is going to blow up. The reciprocal is going to go to infinity. And that is exactly what's happening with cosecant. So as sine goes to zero, cosecant goes to infinity. Now let's look at the other behavior. As sine goes to 1, we're going to be taking reciprocals of numbers that are getting closer and closer to 1. Well, reciprocal of numbers that are getting closer and closer to 1 are getting closer and closer to 1 again. So as I approach pi over 2, sine is approaching the number 1, and cosecant is also approaching the number 1. And in particular, we know that 1 over 1 is equal to 1. So when sine of x is equal to 1, we're going to have 1. And that's why you get all of these points right here. So cosecant touches the graph of sine at every odd multiple of pi over 2. Every odd multiple of pi over 2. And there you go. So that's what the graph looks like. And then, so how do you graph these things? You graph sine first, you put asymptotes at all the zeros of sine, and then you basically just draw these little u's, and then if you want, you can go back and you can erase the sine function. So this is what the graph of cosecant looks like just on its own, reciprocal of sine, and that's it. That is it. That's how you graph it. A couple of things to point out. Notice that cosecant has no zeros. So in other words, the cosecant function does not ever give you the value 0. There you go. That makes sense intuitively if you remember that in order for the cosecant function to give you a 0, the sine function would have to blow up to infinity at some point, which it never does. So cosine will never be equal to 0. The lowest value of cosecant, the lowest value of cosecant will be -1. Oops, -1. And, oh geez, what am I saying? Not the lowest value. The lowest value will go to negative infinity. The highest value will go to positive infinity. What I'm trying to say is that the local minimum of these graphs is going to be 1, or the local maximum is going to be -1. That's what it is. So when you start to look locally at the graph, that's what it is. But literally, that's pretty much it. That's pretty much it for how you graph cosecant. So now with that in mind, let's take a look at the graph of secant. But first, I want you to try to figure out what it's going to look like on your own. So take a minute and look at this graph of cosine and see if you can figure out what the graph of secant will look like. All right, and now say something out loud to yourself. What do you think the graph is going to look like? All right, and now let's figure it out together. One thing I remember is that important property of limits, which says if my function has a zero, then its reciprocal is going to have an infinite limit there. Cosine does have a lot of zeros, just like sine does, right? There's a zero here, there's a zero here, there's a zero here, there's a zero here. There's infinitely many zeros. So if I look at the reciprocal of cosine, which is the secant function, I should end up having asymptotes at all of these points. All those points I should have asymptotes at. Then I know that the graph of secant should basically touch the graph of cosine at those peaks and those valleys. So I should see, let me use red here, the graph should touch right here and it's going to kind of look like this. And then it should touch right here and it's going to kind of look like this. Should touch right here and it's going to kind of look like this. It's going to touch right here and it's going to kind of look like, oops, going to kind of look like this. And so hopefully that's what you were thinking as well. Or maybe I'll do the last one just because. There we go. So if I'm thinking about the reciprocal properties correctly, that should be what the graph of secant looks like. Let's check. Oh, there it is. There it is. It's almost like that was like a better rendering of the graph that I drew, right? There you go. That's it. So this is what the graph of secant looks like. It's just the reciprocal of cosine. And then if you want, you could erase the cosine graph itself, and then that's what the graph of secant looks like on its own. All right. So that's pretty much it. That's how you graph all of these functions. That's how you graph tangent. Oh, did we talk about cotangent yet, though? We did talk about cotangent. Yes, we did. So we did tangent, we did cotangent, we did cosecant, and we did secant. Yes, all right. So now let's do a couple of quick examples. Um, Maybe not so surprising, you can talk about transformations of these graphs, and the transformations are going to behave exactly like the way you would think they would. Um, this number b is going to give you vertical shifts, omega alters the period, and a alters the amplitude. But roughly speaking, the graphs are going to look like the ones that we just saw. So sometimes the graphs that we just saw are called parent functions. You might have heard that in the past. If you haven't, that's fine. We'll call these parent functions sometimes because these other transformations are like their children, right? And children always kind of look like their parents. They look like their parents, they have similar behaviors as their parents, right? So these transformations are like the child functions of those parent functions we looked at. So um, let's see if you can try to work this one out on your own. So let's try to do example one. Graph 3 halves tangent x plus 1 half. And so I want you to take a moment to just think about what you think the graph would look like. All right, now say out loud to yourself what you think the graph would look like. Just even just a property of the graph. What do you think it would look like? All right, and now try to draw it yourself. So think about what the tangent graph looks like and basically apply those transformations to it and see what you get. Okay, and now let's take a look at it together. So I've got this graph on the next slide here. This shows the different transformations. So what do you do first? The period is not affected here, so the period's still going to be pi, but this number a in the front, 3 halves, that's going to change the quote unquote amplitude. But in this case, we don't really call it the amplitude because there's no like maximum height or minimum height, I guess you could say. But it will give you a vertical stretch. And that's because this number is bigger than 1, right? So it doesn't matter if that number is a fraction or a whole number. If it's bigger than 1 in size, it's going to stretch vertically. So it's kind of hard to see with the tangent function, but basically you're going to stretch those waves, the little wavy curves. Wait, there we go, wavy curves. Stretch them vertically a little bit. And then this +1/2 is going to give you a vertical shift. So it'll shift up or down. In this case, it's going to shift up by 1/2. And so that's where we get this. So this is the final graph. Notice that where tangent used to achieve the value 0, it now achieves the value 1/2 because we did a vertical shift of 1/2. And that's the idea. Okay, next. So how do you graph things like cosecant or secant and those transformations? Well, again, maybe not surprisingly, you graph the transformations for sine and cosine, and then you take the reciprocal using that important property of limits that we talked about, and just the reciprocal property of numbers. So as long as you can graph sine and cosine and transformations of sine and cosine, you can graph transformations of cosecant and secant. So again, let's try to do this one on your own. So take a moment and think about what this graph would look like. All right, now just say anything out loud to yourself about what you know about the graph, what you think the graph will look like. All right, now try to draw it yourself. And again, with these graphs, try to draw them nicely, cleanly, straight axes, labeled points, etc., etc. Okay, and now let's take a look at it together. So this is cosecant, which is the reciprocal of sine. So this should look roughly like the sine curve, but it's going to be vertically stretched because the amplitude is 2, or this scalar in the front is bigger than 1, so we're going to have a vertical stretch. And it's going to be shifted down by 1 unit. So pretty much what you want to do is start by graphing the function y equals 2 sine x minus 1. So graph 2 sine x minus 1, and then just use that reciprocal property, and you should get something that looks like this. So let me zoom in a bit here. This over here is the sine curve. Then it looks like what they did was they just drew cosecant first. But then what you're going to do is you're going to have to stretch the sine curve. So this is the sine curve getting stretched. And then it gets shifted down by 1. Oh, all right. Pretty good time to finish here because I think the gardeners are here now. They're going to start making a bunch of noise. So that's pretty much it. That's pretty much it. You'll get more examples on the homework as well. If you've got questions, you can ask them on Canvas. But other than that, time to play. So practice on the homework, and yeah, that's it. So now we've got all the graphs. You know how to graph sine, cosine, tangent, cotangent, cosecant, and secant. And then what we'll talk about in the next section is horizontal shifts, or phase shifts as they're called then, in those contexts. For sinusoidal curves, they're called phase shifts. But that's where we're headed. So once again, thanks for listening, and I will see you all next time.